Okay, I'd like to welcome everyone to the SupportVectors Meetup. The topic today is architecture and guide to fine-tuning and building custom LLMs. Our speaker is a distinguished architect from Cisco. This is Krishnan Ramasamy, and he will be taking us to the, sorry, he'll be taking us to this talk. So now I'm going to yield to him.
Okay, thank you guys. Thank you, Asif. I'm going to share my screen. Okay, thanks everyone for joining. Today, the topic is about understanding the architecture, and that is generally used in, and I did survey, generally used in many companies in order for training, training their LLM and custom LLMs, and as well as the machine learning pipelines. As part of that, we are going to go through some concepts. And then once we explain the concepts, I'll go through some sample architecture in terms of the pipelines, how typically company, design and architect and design the pipelines. And also we talk about not only the inference and training, and also some interesting things about AI agents. So that's all the topics. And since it's a lot of topics, we might spill over. If you do spillover, we do cover that in the next part 2. Okay, so let's start with the question, right? Or what's going on in this industry? What do you guys think about? Now, what would be the top challenge next year in the organization in terms of productizing or productionizing any LLM-based application, right? Some of you already doing some agentic development or RAG development, a lot of these things on. But what would be the top challenge next year? I think number one, I just put it as a scaling RAG application. That is, in fact, maybe true. A lot of RAG application we develop today is morely POC based and getting into the production. So scaling that could be yes, it's an interesting problem. And then second is about knowledge base and graph RAG implementation. So a lot of RAG implementation now considering graph RAG, for much accuracy and then a little bit of predictability, things like that. Yes, there could be some challenge in that. And the scaling AI agents. Do you guys think that AI agents are one of the top hot topic, and then companies are trying to develop AI agents? Would that be a interesting or challenging issue in the organization next year? Of course, the fourth one is pretty simple: monitoring AI agents. So as you think about it, I think most of you probably will be thinking either the number 1 or number 3. So I would think that number 3, which is scaling AI agents, is going to be the key topic as we start implementing the agents, as we think through how these agents could be deployed and monitored, would be the one of the top challenging issue next year. So that's my feeling. So why I'm saying that, right? In this part 1 as well as part 2, we are going to talk about, as I said, how companies are actually doing that in a large, scalable, distributed, fault-tolerant, failover implementation for training and then inference, as well as, fine-tuning. And now, AI agents. Now, how do we deploy, large-scale AI agents, right? With all these characteristics, distributed architectural characteristics. And then can we, use some of the architecture, the industry, have been doing, and then hardened, and then some of the concepts and some of the learnings from other, the distributed training inference, can we use it in the AI agents, scaling the AI agents implementation? So those are the two or three topics in this session. So what we are going to go through, in order to go to that, we need to start some concepts. Let's understand a little bit about the scalability and parallelism in the training and inference and fine-tuning. So once we understand the concepts behind that, then visualizing as an architecture block would be simple, right? So it's more about concept, first we need to understand. And then as part of that, maybe this is more of a reference to you. If you are, some of you are new to this deep learning models, The item 2, I have some reference. You can look at that later, in terms of how the modeling, model training, and model inference scaling at GPU level. And there are various levels of scaling that you need to be aware in this architecture. One is scaling at the GPU level, right? In terms of taking the model, taking the data, how do we train the model in multiple GPU, things like that. That's at the GPU. And then you can say a little bit of the, the NVIDIA stack level. And then above that, there are other scalability, like if you are having a training pipeline and then inference pipeline with the multiple models, multiple data coming in, how do we parallelize, distribute the load? That is the next level parallelization. So we will cover some ideas behind that. And the part of the Ray is an important architectural component, which is heavily used by all the industry. Wherever the ML training pipelines, and then fine tuning, and then inference, the Ray is heavily used as a distributed architecture to enable these things. And finally, we will touch upon. My goal is today is to touch upon how do we scale the AI agents, and we may run out of time. In the next meeting, I'll go through how do we scale training and then inference in architecture or pipelines. So that's the agenda. So what are you going to get out of this session is about some idea about, what is a scalability means, how do we design, architect scalable system, right, for ML pipelines, as well as LLM pipelines and agentic inference pipelines. So we get some ideas about that today. So this is not a introduction class. What I am assuming that is some of you who joined this meeting already knows about RAG, right? What is RAG means, and what are the different challenges faced in the RAG development, as well as scaling up. And I expect some of you, you to be at least know about some of the challenges. And then, of course, if you're not aware of Ray concepts, I'm going to go through that. So you're going to learn about Ray concepts and then distributed, architecture for these things. Okay. Let's talk about this paper. This is for your reference. I'm going to download this as a PDF. You can also look into that. Now, this paper is, as I was talking, there are many levels in the distributed architecture for training and then fine tuning and inference, right? The lowest level is at the level of GPUs, right? And then CUDA layers, where, how the model is being scaled up for training. So this paper is a very interesting paper. If you go to this paper, I'm going to just point out a few concepts in that. And then you can always go and read more on that. So the reason for the introduction is to just give a highlight, right? And the idea today is not to go deeper into that. But at least you guys should be aware of what is distributed training happening at that CUDA layer, right? At the model layer. So what this paper is talking about, right? When you have a model, as you know, nowadays models are big, right? And a few years back until say 2018, in a lot of these ML models are not as big as today. We are talking about now 70 billion, right? 400 billion, right? Parameter models. It used to be much less. At the time, 2017-16 time, even though the model size is less, we didn't have a lot of powerful GPUs as we have today. So the problem of taking a model and try to train in a given GPU was a challenge, at the time, in 2017, as in today. Today, what happened is our model size increased to billions and now trillions, right? And as you know, DeepSeek happened to have more than 780 billion. They say even more than, kind of I think 850 billion parameter models. But nowadays, you are talking about 1 trillion, 2 trillion models. And the problem of taking the large model and trying to train and also inference is a challenge today, though our GPU capability is increasing. So this paper talks about how do we handle such scenarios, right? There is a concept of, it's basically, doing what we call parallelism here, things like model parallelism and then data parallelism and then data pipeline. These are the concept again invented many, many years ago. And then the same concept is used now in terms of training and inferring large models. So when you go through this, just to focus on two things, model versus data parallelism. These are the different techniques in which you can divide the model either horizontally or vertically. And then imagine that you have a big model, 1 trillion model, right? All the 1 trillion parameters cannot be loaded into the memory. So how do we divide that into multiple GPU, right? Divide the model vertically and then get it trained and then converge the data, converge the hyperparameters or gradients. So those are the techniques this paper talks about. That's part one. We don't need to go into detail today, but I'm merely explaining that there is a model parallelism happening at that level. Similarly, for data parallelism, right? If you think about, especially training takes many, many weeks. You would see that somewhere here, they'll talk about training such models on large data set to convergence can easily take weeks or months, right? You have a model, right? But that model can fit into the memory, but there are so many data need to be trained. Then, how do you handle that, right? Can you come up with a parallelism, run the model, right, in training in multiple instance, but you batch the data in a way that you get trained and also converge together. So these are all complex, the layering and the complex, I would say, optimization happening at the CUDA layer, PyTorch layers, right? So for this purpose of the meeting, we will just understand there are parallelism happening at the CUDA layer level, PyTorch level. That is the message I want to say that. How does it influence our architecture? But as we go through the little bit higher level, we are going to talk about the ray architecture. Then we are going to talk about ray tune and then ray training. So it's all higher level architecture. So that has some influence, right? That level. Also, you can specify to the ray, these are my fine tuning criteria. These are my training criteria. So the ray architecture, ray components will trickle down and then manage that CUDA layer in order to do the trainings. So there is a connection between the model parallelism, data parallelism happening at the CUDA level, and then to that higher level ray components. So that's introduction to that. Okay. So having explained some parallelism at the level, let's move on to a little bit about the pipeline, right? See, when we talk about before ML applications, all of us or most of us are well versed with scaling different types of other applications, right? Data intensive applications, enterprise middleware applications. So we have learned a lot of interesting techniques in developing distributed, failover, fault tolerant, scalable, and then redundant. All these systems, we have been doing it, right, one or other way. So there is a lot of techniques created out of all the SaaS companies in enabling that scalable distributed applications, right? For example, in AWS, we have API gateways and partitioning on data, Cassandra database at the database level. And then at the API level, you can have scalable distributed duplicate systems. A lot of these techniques, architecture evolved over the time. But how about ML applications, right? And then as we are maturing in that in a distributed enterprise SaaS oriented application, the ML applications started coming, right? And initially it was a pretty simple pipeline, as you see here, right? It has a pre-processing, it has a training block, it has a fine-tuning block, and then serving block. You could imagine in the beginning, it was mostly a script-based approach, right? And then as the time goes on, obviously we need to run it in a production system. And then we started thinking about how do we distribute during the training and then fine tuning these ML applications. So consider this a pipeline. You don't need to visualize this in LLM or ML or agents. Imagine this is just a ML pipeline right now. So how do you create distributed parallel fault tolerant failover systems for ML applications? Right? It's slightly a different problem. The problem here is, unlike the SaaS applications, here there are two distinct phases. One is the training phase. You can consider as during the development/training, and then there is a production inference phase, and then there is a feedback loop, and then fine tune and retrain, right? We can consider as a third phase. So there are unlike SaaS, here we have multiple phases are here, right? That's one difference between the ML based application versus SaaS based applications. And what does it mean? That brings a lot of challenge. Unlike the SaaS based developing the distributed application, here there are different types of technologies are involved, right? During the pre-processing, as you see, you might need to use, right, for scaling, right? Good scaling, good system, you need to use Spark to process this lot of data coming from different sources in a scalable way. So that's a technology used, for scaling the data processing or data processing, pre-processing side of ML pipeline. And then during training, obviously training, as you would know, PyTorch is the number one, the layer for training, right? And though TensorFlow is there, PyTorch is the prominent training layer. And then, when you think about what do you mean by, how do we develop distributed scalable training, right? That's an interesting challenge. So you might need to develop your own way of managing the distributed systems using the PyTorch. It is a challenge because there was no framework available. You have the PyTorch library available, but how do you make it work in a scalable, fault tolerant, failover, all those characteristics that we attribute to the distributed systems. And then during the fine tuning, the same problem, or tuning. Tuning here refers to hyperparameters tuning, and as well as if you are from the normal ML based application development, you might need to experiment with a lot of parameters, right? There are 50 plus 60 plus parameters, hyperparameters, and for every parameters you need to train and validate and see what's the right thing. So it's a very cumbersome process, and fine tuning and ensuring that the data quality matches with what you need. So what is a layer which can help us to architecture our layer can help us to do that easily? That's one challenge. And things like batch prediction, and then serving inference. Serving is inference. Now, how do you serve thousands of instance that is accessing? How does that ChatGPT, think about ChatGPT, OpenAI, how do they take care of millions of users trying to connect to their backend system, right? And we don't know their architecture, but you can imagine their backend inference has to handle billions of users. What is the architecture of that? At least in enterprise, though not billions, we need to worry about thousands and thousands of connections coming. So these are the challenges. You can put it in a way that there is no single unified system was available to develop this distributed, scalable, right? Fault tolerant, failover, all kind of the characteristics. So that is where the Ray is coming in. So now that we know the challenge, here is a solution. So Ray is a unified framework for productionizing the distributed ML, and now we can say LLM, and also you can add agents applications, right? So that's a key thing. So this is the starting architecture. This is not the end architecture. This is a starting idea for you to realize that, oh, we need a Ray type unified framework to make all these 5 components of ML, LLM, agentic applications in a seamless, on a single coherent way, right? That's the Ray. So the story is, the message is, we need to be understanding Ray in order for us to know how we can build that such application, as well as how companies are already using Ray, like Uber, for example. They are using Ray in all their scalable and all their ML applications. We will touch upon their architecture. All right. What's Ray? Now you got an idea. Ray actually solves a great problem. It unifies a different framework into a single sort of a framework. What is Ray? A general purpose library for distributed computing. I mean, I won't call it as a library, but okay, fine. It's a framework. Now it provides not only framework, it provides as well as monitoring systems. You can look at that, what's going on at any point. So it's a little bit more than library, but now it's called Ray. An ecosystem of native libraries to scale ML workloads and runs anywhere, of course. And also, interestingly, it runs underneath. It can use Kubernetes cluster for its management. So there is an idea of Ray over Kubernetes, right? That's also one of the popular architectural stack. Okay, that's Ray. And what's the history, right? Who started the Ray? It's pretty recent. As you see, it is in 2016, right? It's not too far away. I mean, too long away. So it started as it started as a class project. Wow, in Berkeley. I mean, at the time, 2016-17 was the time the ML applications in our normal CNN based or NLP kind or regular Python based classification and supervised engine, right? And then unsupervised cluster. Those are all a little bit maturing, right? At the same time, it matured, and then it was trying to go into large scale production. So the Ray started as a unified application framework to solve the normal ML problem, not LLM. At the time, there was no LLM. To solve the challenges faced in productionizing those ML applications, right? Google has so many. At the time, Uber has so many ML applications, things like that. And then in 19, they formed the company Anyscale. So now it's called Anyscale. And they have two versions. And Ray is still there as an open source, and Anyscale is an enterprise version you can call. So, but you have access to both. In the enterprise version called Anyscale, and then Ray is the open source. Okay. All right. Okay, now I'm going to go a little bit quickly, show some examples of Ray. Ray, as we know, it's going to be unified framework, right? What is that unified framework means? Okay, it's very simple. Ray enables you to develop a distributed, right, task management. And distributed, you can say actor. In the word used, actor is, they used in a different context. So it's basically allow you to develop. Here I'm using the word develop, to develop distributed applications, but later in the production, it's automatically scaled by the Ray framework. So that means first, when you develop your application, you need to apply the Ray library, right, with annotation. And then when you develop the application with the Ray concept behind it, it's going to be distributed and managed automatically in the production. So first thing is to understand few things about Ray, and then in the production, it's a magic, right? When you apply this concept in the development, how it's managed in production is pretty magic. It's taken care of by the Ray. So I know this is going to be a little programmatic, but I'm pretty soon I'll go into high level. But this is very, very important concept. Ray provides automatic way of that's called distributing your task, right? And then it allows you to um, manage your task in the distributed cluster anywhere, and then combine the results from these distributed clusters. And then while combining it, you can do it in a sequential parallel way, and then finally produce the results back to the end user, right? I mean, this is a concept. When the Ray was developed, it was, there was not a thinking about fine tuning, training much. First, they developed a basic distributed framework. Then this is applied to the tuning problem, training problem, and then inference problem, right? First is the basic concepts. So in this, for example, right, if you're coming from Python background, and this is an example of how you're developing a distributed application. So here, what you're doing is you're defining a function called f of x, and you're doing something, and then you're returning r, right? And then here is your main function. In the main function, let's say the main function is running in a node, and then it says f dot remote a, and then that means what happens is it is going to instantiate a function called f in any node available. Okay, I mean, we don't know, but Ray knows that. In whatever node is currently free, node means you can imagine there's a machines. There are 10 nodes, there are 10 machines in the distributed cluster. Ray automatically knows, okay, I need to run this function f of x. Let me figure out the correct node, available node, and then run that. So it's a function of Ray. Similarly, when the code says remote B, it takes any available node and then run the function called f of x. So in any available node, right? And then this is to get the results, right? And that's a concept in Ray. What happens is when you do the remote A, this worker already runs. Imagine the worker already runs a function A. That means what? It copies the code. You can imagine that it copies the code into the worker node, and then it then associate when it runs, it's run, right? I mean, in a distributed or remote way. Similarly, remote B, it runs in a different node. Imagine worker is running in a different node. In the example, you can imagine this worker is running node 1 and this worker is running in node 2. So that illustrates that there is a distributed computing is happening. And then ray.get, essentially when you say ray.get, it gets the data back into this process space. That's what ray.get. Why do I am saying that, right? This is a foundation. This is called a task level distributed work, right? So this is a very, very basic. This is how later we are going to scale all our training and inference and agents. Things like that will happen magically once we understand few concepts. So in this, a task can be scheduled remotely and can be executed remotely in any available node in the distributed frame in the cluster, and then results can be get to this process space. That's one concept. And there are a few other concepts I'm going to go through, which is state versus state plus, things like that. That's a foundation for again the architecture, right? Okay. Now that we kind of explained a simple function in the distributed architecture, think about what are the natural questions will come to us. I mean, I'm going to tie this with agents, right? My goal today is make you all, including me, to think about the distributed architecture in Ray, and then take it to our problem domain, right? Our problem is how do we scale inference train. Today, we are going to talk about how do we scale AI agents using this Ray foundation blocks, right? And then in the next, part 2 of the series, we'll talk about, inference, how do we scale inference and training. Okay. Let me look at the time. How are we doing? Okay, we are doing good. So now let's talk about the Ray has so much things, I explained a very simple concept in Ray, which is a Ray task. Like Ray task, and there are a few things, Ray actor, I'll be talking soon. So those are all the foundational blocks of the Ray, right? And then there is a little bit higher level, which is called Ray tune. There are libraries in Ray, which is called Ray tune, and then Ray serve, and the Ray train. You might ask, the Ray core is the one I was trying to talk. Imagine this is a Ray core, part of the Ray, right? These are all the core functions in the Ray. And then there are higher level thing called tune. What is Ray tune? Ray tune is a higher level Ray functionality, which has so many functions to run or tune your ML models. How do we How do we optimize? How do we run and then test, right? In the ML models, in the ML models, as you would see, the hyperparameters need to be tried out and then see the results and finally choose the best hyperparameter, more of an experiment. How do we, without the tune, you might need to write those experimental code for each parameters, do this check, and if it is so, if it is fine, then stop there and then consider this a right model, a parameter for the right model. So these are a lot of this higher level um, experimental logic, business logic, is abstracted into the fine tune. And then, obviously that means it will make the fine tuning layer much simpler. In a couple of lines, you can fine tune. And then the ray fine tune layer is going to be magically doing all the business logic, you can say, in terms of the specific fine tune. Similarly train and similarly serve. So the whole idea is they are trying to make, they means here the ray and the any scale is essentially trying to commoditize, make it so simple, for all of us to develop and then productionize in the training and then serving. At the end of the day, you would see it is like 4 or 5 lines of code. So a lot of magic happens inside these functions. Okay, here are something you can see in the top, right? What are the different things supported by each module, right? So, and talking about the Ray, there is a conference is coming in May in New York. It's interesting conference. I'm planning to go. But if you are interested in this domain, it's called Ray Summit 2025. It's going to be a fun conference. Okay. So what are we talking now? So I think we have some idea about what Ray, how Ray and low level components versus high level functional components. All right. And who is using Ray? Of course, everyone. Everyone is using Ray. If you are in ML production, if you are productionizing scaling LLM applications, Ray is one of the choice. I don't know any other framework is being used, but the Ray is obviously used left and right in most companies. Okay, so now that the founding blocks, another couple of slides to understand this in a slightly different way, right? I mean, if you're coming from a visual person, as you see, there are 3 concepts. The one that I showed, Ray task. Essentially, behind the screen of that, there is a scheduler, right? And then there is an object store. So, and then there is a global distributed store. So these are the 3 concepts: scheduler, object store at each node level, and then across the cluster level, there is an object store. So 3 concepts. So through that, the Ray cluster exchange data between different nodes if needed, and then manages a global store for global access to, I say, global data, right? So that's and they call Raylet. That piece of the code in each node that manages a scheduler and object is called Raylet. Okay, so now, well, you're welcome to read good Ray books, design patterns. But I think the a couple of key concepts. Now that I explained very simple example, which is nothing but the task parallelism, right? The parallelism I talked about is basically stateless. It's very simple task. If you can remember, I run the function A, function B. It can go to any worker node and then run, comes back, done. And there is no state mentioned or they maintained that particular task at the worker node level. That is a stateless execution, right? And yeah, it is good for executing the task. But if you want a little bit stateful, in other words, you may come to know when when you're trying to productionize scale the AI agents, perhaps you may need to maintain some state when the AI agents. Today we are all, even in the support vector, we are all learning AI agents. As of today, we are running a little bit locally, running like 5, 6 agents. But imagine you need to run thousands of agents, right? And then some of these agents need to maintain a state, and then it can come and go. Things like that happens, if you're using Ray for that. Ray plus AI agents is a hot topic, right? That's what we are trying to understand today. So then you need to maintain some states, right? So that is what Ray objects provide. Ray actors is an extension of that. It provides a stateful service on a cluster. So these are the key words: task, Ray objects, and Ray actors. So once we understand, we can easily build higher level distributed LLM applications. Okay, so again, a little bit detail. You're welcome to read more with this presentation. I will check in, but we talked about a remote, Ray remote, right? It's a remote function. It's a stateless, and then this is a typical way to do that. Similarly, there is a call actor, right? If you can say, you can make some counter as an object, and then if you say Ray remote, and this is a class-based Ray remote function, you can call remote objects, right? And then there are, of course, the idea that you can execute the remote functions in a parallel way and sequential way. So today I'm not going to go into that. That's a little bit detailed Ray understanding, but just imagine that there are many ways in which you can combine the order of Ray execution remotely, and then combine with the main program. And then there is a concept of, as I was saying, this is a very foundational core part of the Ray. Each worker can share, can access to its node memory, can also have access to the global memory. Global memory means across the distributed architecture, right? This slide illustrates that. If, for example, this worker process has access to X and Y, and another worker process within the same node, within the same machine, can access to the shared memory of Y, and then Z is that. All right, that's the idea here. So this is an example of how distributed objects being accessed without getting copied. See, one of the promise of Ray is in the distributed nature, the distributed sort of the workload, it is taking the pain of copying, right? Let's say you are running an agent in one node with Ray as the actor. And then let's say that you want to access some tools running on a different machine, right? And then this data need to be copied there or between the agents. The Ray framework provides some capability on its own, using its own IPC mechanism to copy the data. So we are offloading some of the challenges. If you're developing the agentic application in a distributed way, you can rely on Ray to manage the data management between, right, two different agents using the distributed architecture. Okay, so these are all in details, right? We can go. Why I'm saying this is, so when you're thinking about developing the production distributed application using Ray, so the message here is, during the development you need to be adding these concepts, right? It's not that you develop agents, let's say, without thinking about the distribution, and then you can just port it like multiple process and all. No, here you need to use the Ray framework as part of your development. Think about the architecture, think about how it's distributed, and then in the production it comes free for you, right? That's a key theme we need to remember. All right. Well, I'm going to skip this. Why Ray Tune is powerful. Of course, I've been talking about why it's powerful. Some other thing is, it provides, once you code for it, it provides a distributed training out of the box, and then it provides a schedule support. It provides parallelism and scalability. It provides logging and monitoring. All those things it provides out of the box, right? Once you know how to develop the Ray application. Okay. All right, let's skip it. Now, let's switch the topic here, right? So what did we do so far, right? We touched upon concept behind the array, and then yeah, again, it's not too detailed. It's just at the high level we understand array is a distributed architecture, right? Enabling specifically ML based applications to be developed for scaling. And then we touched upon few concepts like array task, and then array remote, and then array actors, array objects, and array things like that. So with that in mind, now what I want to think about is, we are going a little bit higher level, right? We started the CUDA level parallelism just for understanding purpose. Then we talked about the array architecture, why we need array. We talked about that. And then now we are moving a little bit high level. So now we are going to develop agents. As I was saying, agents are interesting. So that's why I want to cover today. In the next part two, I will cover the inference. Inference means, like, for example, how the ChatGPT developing the inference server, right? With the distributed inference server. We'll cover that. Okay. So building scalable agents. This is a presentation in YouTube. I have mentioned that in the document. You are welcome to view that again. But this I'm walking through this presentation in my own way. Okay. So this presentation is from, of course, last October or November, something like that. And then they developed something called array-based agent called R agent. This group, Ant group, okay, and then they developed the framework called R agent. Essentially, they thought about, how do we scale the AI agents? The same problem I'm trying to address, right? I'm trying to learn today, and some of us, would be facing the same problem in the near future. So how do we scale AI agents, right? AI agents, if you're aware of AI agents development, by the way, in support vector, there is a course, right? AI agents course. We will touch upon these things, scaling the AI agents. So that is a big problem, right? Out of one, if you talk to 1 out of 10, 10 people today who are, developing agents, I'm sure maybe even one person has not thought about how to develop scalable agents, how to productionize. All right. So this is a good paper or good video to start thinking about it. So in other words, can we use the Ray framework for developing the agentic, AI agents? That's the main theme of this video presentation, which I'm going to walk through. So this session offers valuable insights for developers and organizations looking to harness the power of AI agents at scale, right? So, and I don't think we have access to RA agent, right? But this idea gives you to develop RA agent, right? Something similar to RA agent. Okay. So let's go into that. And what's the time now? Yeah, I think probably another 15 to 20 minutes will be on time. So I'm hoping you're all aware of agents, but this is the typical agent means, right? Agents have for according to this presentation, there are different characteristics or different definition we can give, but I think this covers pretty good. So every agent we develop will have some kind of profile, the persona behind the agent profile, and then it is defined as prompts. You can say, if you are coming from crew AA, you can say backstory and then role. So these are all things about the agents. And then we do have memory. Memory is an important concept, right, in agent. And then every agent has to, agent means it has a ability to plan, right? Today you may be using the higher level framework, which is maybe doing the planning for you, like create, taking care of the planning, right? And in some other framework, you need to instruct the planning properly. So the planning is happening at the agent, right? And then also action, right? Once the planning, during the planning, after the planning, when the agent runs, it needs to act. You might have heard about the React framework, right? Sense and observe, and then act, and then go into feedback loop. React framework, React pattern. Sorry, not framework. React design pattern. So these are all the 4 key components. Okay. Why I'm saying that, right? Now, how do you develop scalable? Now agents, you think about you're developing in your laptop, right? All these things are running in a single process space, right? The planning is happening. When the agents run, the planning happening in the same space, process space, and then action probably happening in the same process space, and then memory, of course, it is part of the same space. Well, that is good, right? But can we, how do we develop scalable version of that, right? Can we have a planning running in one process space versus action happening in a different node, right? Where the compute is needed. So that's where you start thinking about distributed load, right? So I know we are all still learning how to develop agents in a simple way. While we are doing that, we are also start thinking about, you guys, we should start thinking about how to run it in a parallel way, distributed way, right? So that's sort of the inspiration I'm trying to bring in today. Keep thinking about it. But this video gives you some ideas. All right. What is naive agent does, right? Naive RAG agent. It's called RAG agent, but consider it is an agent, right? Uh, I know there are a lot of definition for agent. Agent means what if you don't if it doesn't collaborate with other agents, it's not called agents, right? And sometimes there is a definition for that. But in this case, simply assume we are talking an agent which has some responsibility, not a collaborative agent at this point. Well, okay, this is an agent, and as you see, agent. This is a good diagram, a good visual diagram. An agent has a memory, right? Agent has a tools, and agent has the following: react. It is observing. Observe me could be anything, right? It could be a sensor, it could be a chatbot. You type the chatbot, AI assistant, some question, right? So then your agent is observing what you typed, and then it starts thinking, the agent, and then of course there is an LLM behind that. So whenever we say agent, it has to make some reasoning and autonomous decision, right? That means it needs an LLM. So this arrow means LLM here. So why many for the agent to think, it needs LLM. And then for the agents to act, yeah, it may need LLM, but it also needs some other things called tools, right? So it needs the tools. Using the tools, it has access to the knowledge. Imagine nowadays we are talking MCP as an interface to the tools, but let's say tools is a way to get external, some knowledge. And then it can also query the way in this diagram, the way they wanted to put it in a different color is to illustrate to you that there are different computational aspect of load happening, and then there is an aspect of disk IO is happening, that's a green color. There is a concept of network IO is happening, that is like query. So here the focus is now how we are thinking in a distributed way, right? So in all these 3 aspects, right? In the computational way, how we can scale. In a disk IO way, how do we scale the agents? In a network bound, right? How do we scale? So that's the angle I'm looking into that. Okay. So I think the problem is now set, right? So far we know how to develop agents simply in a single Python code. And then now we are asked to think, distribute that load. All right. I mean, according to this paper or video, there are many user complaints. At the end of the day, we all know that agents are not responding, right? It's not utilizing the GPU properly, right? In a distributed cluster. Things like these, there are a lot of GPUs available, but your agents are very slow. So if you don't have a Ray framework, let's say your company is giving to you, let's say 10 A100s, and then but your agent is so dumb, it's not able to use those distributed cluster, then question comes to us. You have so much powerful GPU, but your agents running in a single space, no, it's not working out. The application is doomed, right? So we need to know, we need to utilize the GPU properly, right? And then run the agents workload. Agents are very creative, of course. This is this for the author to say that there are so many agentic applications can be developed. So in this particular case, the who are presenting, they have a agentic dashboard there. You can create thousands and thousands of agents, right? And so their system allows you to create thousands of dynamic agents, and then all of them is running behind the scene. Okay, so when they wanted to develop this, I'm sure, they would have thought about how to develop this scalable agentic runtime. I'm sure they might have considered about obviously Kubernetes and then LangChain and then Ray, right? Uh, so this is their comparison, right? This is a report from the author. Of course, if you have Kubernetes, we all know, very great system, proven system, used for a lot of scalable distributed workloads, right, in enterprises. But one thing it comes to me, which I'm resonating with this author, is it has a high learning curve to develop in a normal, not only the develop, even managing the Kubernetes cluster. Still, it's a complexity is there. It's not pretty straightforward. When you take that and then develop AI programs over to that, I think it is more complex to do that. I mean, that's why Ray is coming in. But here, just a comparison. Kubernetes has a lot of cons, which may not suit us. LangChain is good. LangChain, I never thought about how to scale. It is a chain-based application. I never able to visualize how to take the LangChain chain concept, right? That is in a single process space to make it work for distributed application. I don't know. LangChain is thinking. Maybe they are thinking to somehow make it as a distributed chain, right? I don't know whether it's there or not, but it's hard to productionize. But that's where Ray comes in. Ray already has an inbuilt a lot of this framework, it providing the basic founding building blocks. We need to know how to use it, right? So Ray provides that opportunity for us. That's a pitch here. Okay. Again, this is coming from this company. What is the company? I forgot. It's called Ant Group, right? Ant Group. So these are coming from Ant Group. So they thought about this stack, right? And if you look at the stack they developed, Ant Group developed, they have a Kubernetes cluster here, and then they have a Ray stack here, right? And then they develop their own R agent. That's a piece. We can get some ideas and see whether we can develop something for you, for your need. And then our agent is a agentic SDK which powers higher level applications. And also they said these are the agent applications. And part of that is they said you can use any of the agentic frameworks. That is something I'm trying to understand. But the way you can read this is important thing is the agentic application you develop using the Python framework will use the R agent SDK, which internally implements the Ray-based approach for the distributed agentic development. I think this is a key message for you guys to develop the scalable agentic application. Okay, let's go through the example, right? So now if I have shown this slide, without introducing the array, it would have been much more too detailed, right? To intensive. But now that you guys know what is Ray task and Ray actor, why not we develop an agent as an actor, right? So this agent is an extension of the Ray actor. It has a functionality for failover profile. It is going to something use message queue. I'll come to that. And then inside that agent, you have the React pattern. The React pattern is the agentic, simplified agentic. It is an agentic pattern, right? So what they say is, what this author says is, the higher level, the SDK, which I mentioned, has implemented some of these functions. You basically call base agent, and then it will have register tools, things like that, right? And then React agent is derived from the base agent. And then, so when you go into this base agent and React agent, you're not seeing any Ray specific annotation set because it's inbuilt into the SDK. So we are talking about uh, some of the middle level layer React agent. Okay, here you have reason and invoke. Stay at this level. When we look at the application, then we'll come back to this. So this is how what they are saying is inbuilt. These functions are inbuilt in this case of this author, right? Let's look at an example now. Okay. Let's start from application so that it's easy for us to visualize. Let's look at the bottom layer here, right? So you're in the main function, right? You are defining an agent, and then agent, when we start an agent, we always know agent needs a tools, right? You register tools. In this case, you are registering a tool called index underscore dot. This tools, as you hear, as developed as a library. And then of course, then it's available to your main program, your agent program. And then your first thing you are doing is you're registering the tool, and then you're running it. So this is a level of abstraction in this case of example, right? Okay, now let's see what happens inside that. This is the most important diagram to visualize. So once we understand this, we understand that, of course, we can tie what we talked about distributed versus the agents. Here, what's happening is, let's say you have this code, this code, main code. Let's say that it's running in, let's say, node 0. Let's say you have 10 node cluster, right? In the 10 node cluster, your main agent, your application program is running in node 0. I'm just making up. In the node 0, now you're defining this application, this Python code is running. You're instantiating one agent called React agent, and then you're associating with some model, right? And then you're registering the tools in this case, index doc, semantic search, lexical search. And then you are invoking, okay, this is where the distributed load comes in. Now you're invoking some loading the doc, and then asking a question. Think about what happens, right, when these two things run. Uh, Again, you need to visualize, this is a higher level abstraction given to us. It's basically a React agent. So inside that, they used our Ray concepts that we talked, right? Ray actor, Ray task, Ray objects. A lot of these are used inside this program. But the main message you need to understand, when we do the invoke, right, it can run in any node in the cluster, right? When you say agent.invoke, the Ray framework is taking care of taking the agent code, right, in any cluster that is available to you or any node that's available to you, and then it is invoking this function. And that function, which may in the node 2, where the you say capacity is available, compute capacity is available, it runs in that node and then get the runs successfully and comes back. Similarly, task 2 could be running in some other node. It could be available based on the availability of the compute. It may be running in the node 5 and gets you back the results here. So that's a key, that is a key foundation, key message today's meeting, is by knowing, by developing framework like this, our own framework, something like React agent we can develop, which internally uses array concepts to run such functions for you, which runs in a distributed cluster. So that's the bottom line for today's meeting. And then now you can extend the same thing. Now once we visualize this, obviously you can run collaboration multi-agent app, right? And then in this case, and they had developed another layer called Meta GPT agent layer, which allows you to multiple agents to coordinate, collaborate, right? Sometimes the agents need to share some data. Suppose in the crew A example, you have a crew and you have a supervisor, you have 5 agents, right, in the team, and they may need to share something, right, pass on some information to the other agent. um, in the So imagine how we can do it in a distributed cluster way. So this author has developed a Meta GPT agent, and then which takes internally it uses raise distributed object store, right, and then message passing capability to do that. So that's architecture. So for example, if you can visualize you're writing a collaborative agents in a distributed cluster environment, this is a sort of the architecture we can think about it. So in this case, they created an environment as a function inside that Meta GPT agent, which is nothing but another component which manages the message queue, right? If we don't have that, I know some of the team members in SupportVectors, they are trying to develop message queue based communication across different agents, right? But if we develop a library like this, right, and then it can be the common abstract way to do these things. So this is an example inspiring us to develop something like this for our collaborative agents in a distributed cluster. All right. I mean, this is the example of that, right? And you see here, join. If I had to look into this code, the Meta GPT agent, it essentially doing the race. If you remember the sequential versus parallel execution, right? It will be implementing something over that, right? All right, and then finally, this is when this is a YouTube. You're welcome to know more about that. And then there is a Uber next week or next time. I'm going to go through this Uber. Today we run out of time, 8:18. Okay, we can stop here. We generally want to go about an hour. So in the part 2, I will talk about how Uber and how some of the other companies, not agents, I'm going to how they develop the inference scaling, scalability architecture for inference and training. I'll go over that. So what did we learn today? I'm just summarizing. So we got some, I hope you guys got some idea about ray concepts and why that is very important, right? For us to not only to develop scalable, right, distributed, fault tolerant, failover applications, inference pipelines or fine-tuning pipelines. It is also essential for us to develop AI agents at scale, right? So here are some ideas coming from that ray video I shared, and then we can expand on that and develop our own distributed application for this, for your chosen agentic framework. Okay, and next week I'll go through the Uber training architecture. All right, with that, I'm going to stop here.